Hey everybody, it's Janae here. So I decided to come back. I wanted to get back on here just so that I can stay focused. I do think that I did a pretty fair job during the first video that I made today for this study session. So the topic was heat, and this was for Physics 100. So for this particular one, I kind of wanted the videos to correlate, but for this specific video, I will go through the change of phase, and then also thermodynamics. So I'm going to go through the two slides for those. And then I should be done. The goal is to get finished within an hour. So if you have any questions or any comments, please feel free to write it in the chat. I will start it off by simply saying hello. So you are free to respond. All right, so I did like the music last video that I made. I did have jazz music on. So I will try, let's see. Do you want music on? You know what? Let's just not do the music for this one. We won't do the music, and then I'll compare and see which is better. Is it best to have music or not? So the slide that I'm going to go to, again, it's change of phase. So there's different phases. There's evaporation and condensation. There's a melting phase and a freezing phase. There is energy and phase change. So there's different phases that we have, from evaporation to condensation, from melting to freezing. So energy and phase change. Phases: gas, solid, liquid, and plasma. So energy of the system. So there is a really cool picture. It shows you what it will look like. So for liquid to turn to a gas, it's through evaporation. And then from a gas to go to a liquid, it says deposition. And then from liquid to solid, that will be freezing. And from solid to liquid, that will be melting. From liquid to gas is evaporation. I'm sorry, I said evaporation. It's evaporation. And from gas to liquid, condensation. So if you wake up, you may see like a little bit of water on the grass. Some people know it as dew, DEW, but another name for that is condensation, from a gas to a liquid. And then from a gas to a solid, it says deposition. And from solid to gas, it says sublimation. And then there's also plasma here on the list. From a gas to plasma is ionization. And from plasma to gas is deionization. Phases depends on temperature and pressure. So phases of water. So liquid water, ice, triple point, water vapor. So it's going to depend on the temperature and the pressure. Changing the phase almost always requires energy transfer. What are 4 common states of matter? So solid, liquid, gas, and plasma. How is the kinetic energy of the molecules different in each state? And how can you change a block of ice to steam? So a block of ice to steam, we know we want to change the phase. We're going to have to change the temperature and the pressure. So liquid has a higher kinetic energy, faster particles than solid. So think of a solid and then think of a liquid. So the liquid has higher kinetic energy, faster particles than a solid. So solid has the lowest energy. Gases have more energy than liquids. And plasma have even more energy than gases. So which has the most energy? Plasma. Change ice into steam. So we're going from phase to phase. Change ice, solid, to steam, to a gas. So not even to liquid, but to gas, ice to steam. So lower pressure. If you boil it, so you can boil it, and you can go from ice to steam. So just remembering that the solid's going to have a lower energy, and then the liquid will have more energy than the solid, and a gas will have more energy than a liquid, and plasma will have more energy than a gas. Evaporation and condensation. So change of phase from liquid to gas. So again, thinking about the picture where you have evaporation. So how do you get evaporation? You go from a liquid to a gas, and that is evaporation. Well, if you do the opposite and go from gas to a liquid, well, that's condensation. Or as we mentioned, if you go outside in the morning, the grass is a little wet, we know it as dew, D-E-W. That too is condensation. Change of phases from liquid to gas occurs at the surface of the liquid. Evaporation and condensation. When evaporation occurs in a dish of water, the molecules left behind in the water are less energetic, have decreased average speeds, results in lower temperature. So all those things apply. So when evaporation occurs, so evaporation is where you have liquid and then it's going to go up and turn into a gas. So when that process happens, then you have less energy. It's less energetic. The remainder that's left behind in the water is less energetic. You've decreased the average speeds, and the results in the lower temperature, they're different. It's a lower temperature. Evaporation and condensation. I'm doing such a good job here. Feel free to comment in the chat. Again, this is a review. So we're going through the change of phases, and then the next one's going to be thermodynamics. We're talking a little bit about the different phases from liquids to gas, gas to liquids, solids to liquids, liquids to solids, gas to plasma, plasma to gas, solid to gas, gas to solid. So we're going through all those different phases. So examples, getting a shot, pigs taking a mud bath, dogs painting or panting, people sweating, damp cloth on your forehead. So evaporation and condensation, thinking evaporation is something that's wet. It evaporates, turn into a gas, and we go from a gas, we can turn it to a liquid. We can call that condensation, and we might know that as dew when you wake up in the morning and you see that the grass is wet. So getting a shot, you might begin to form condensation. Your body starts to sweat. So maybe pigs taking a mud bath, maybe they're hot. They take the mud bath to cool themselves down. So dogs panting, again, their body is producing condensation, the sweating, people sweating. You might put a damp cloth on the forehead when it's hot. So those are times when condensation is in fact occurring. So condensation causes warming. So you feel cold. Thinking of when you're in a shower, you get out of the shower, you feel cold because the water on your skin evaporates. So when you get out of the shower, that's why you feel cold, because the water on your skin evaporates. So that's interesting. You warm up if you step back into the shower because the water vapor condenses on your skin. So that's interesting. It's going through the different changes of the phases. So that's interesting. So when you feel uncomfortable on a muggy day because water molecules are condensing, from the atmosphere onto our bodies, preventing evaporation. So we feel uncomfortable on a muggy day. When we say muggy, it's probably going to be like a icky, sticky, like a humid, dry, hot day. And so condensing from the atmosphere onto our bodies, condensing from the atmosphere to our bodies and preventing evaporation. So it's muggy. I don't know if you can visualize that, where evaporation is prevented and it's just an icky, sticky day and it's like, go away. Well, somehow, the atmosphere didn't go through all the steps for evaporation and it's muggy. So when a liquid evaporates, it gets cooler. When a liquid evaporates, it gets cooler. So that's like the person stepping out of the shower and you have water on your skin and you feel cool or cold because the water is evaporating on your skin. And so it's losing its energetic molecules. So when a liquid condenses, gets warmer, so that's like stepping back into that shower, you're gaining, or it's gaining its energetic molecules. So why does 95-degree Fahrenheit feel cooler on a hot, dry climate than 95-degree Fahrenheit in a hot, humid climate? So why does it feel cooler in a dry climate? Why does 95-degree Fahrenheit feel cooler in a hot, dry climate than a 95-degree Fahrenheit in a hot, humid climate? So sweat and evaporate more efficiently. So here it's saying that if it's humid, hot and humid, then if it's a 95-degree Fahrenheit and it feels cooler and it's hot and dry, so forget about if it's hot and dry, then the sweat will evaporate more efficiently than if it were hot and humid. So why do the clothes that are hung outside dry better on a windy day? Evaporation. Wind carries away wet molecules, speeding evaporation. So evaporation and condensation. Sometimes evaporation takes place beneath the surface of a liquid, causing bubbles to vapor. So sometimes evaporation takes place beneath the surface of a liquid, causing bubbles of vapor. That's interesting. Evaporation and condensation. Boiling depends on temperature and pressure. Higher pressure equals higher boiling point. Lower pressure equals lower boiling point. The process of boiling water tends to cool the water. Melting and freezing. Melting, a solid absorbs heat. The molecules have more energy and speed up. The molecules break free of active forces and the solid becomes a liquid. So the molecules break free of attractive forces and the solid becomes a liquid. So anytime you have a solid becoming a liquid, there was a change in the phase. Freezing, a liquid loses heat. Does that make sense? Liquid losing heat. So heat is being emitted somewhere else. And so that liquid is starting to get colder. It's cooling off and it freezes eventually. The molecules lose energy and slow down. So if you're losing heat, then the molecules lose the energy and it's going to slow down. So attractive forces take hold, causing cohesion, and the liquid becomes a solid. When an ice cube at 0 degrees Celsius is heated and melts to form water. So ice cube, 0 degrees Celsius, when it's heated and it melts to form water, that is an example of change of phase or energy and change phase. All the heat energy added is used to change the ice at 0 degrees Celsius solid to water at 0 degrees Celsius liquid. Heat energy used to change from solid phase to liquid phase is called heat infusion. Heat of fusion from the solid phase to the liquid phase. When all ice is melted, the heat energy is used to raise the temperature of the water. So all of the ice is melted. Heat is used to change the temperature of the water.
Think you studying? Hey, all you do.
100 cows of energy are needed to change the temperature of 1 G of water from 0 degrees Celsius to 100 degrees Celsius.
What is that, physics?
Yes.
Okay, I'm smart. I should go to school. What?
It's my brother, you guys.
I should go to school.
You should go to school. If I can do this, anyone can. By the way, I graduate, you guys. I'm going to be graduating in the spring. I'll be from Washtenaw Community College. I'll be going to Eastern Michigan.
Hey, why you
so I'm excited.
Was she acting up? She in your way?
No, she's fine.
Was it? Did I close the door on her, or did you do that? I must have did it.
She probably did it. She probably tried to get out or something.
Oh.
So yeah, I'll be graduating. I'm so excited. All right, feel free to comment in the chat. I'm going to put some music on for you. Hey, Nana.
Years of war have pushed me.
Okay, so when water at 100 degrees Celsius is heated, it boils to form steam. So water, think of water 100 degrees Celsius. It's heated, it boils to form steam. A change of 1 gram of water to 100 degrees Celsius to steam at 100 degrees Celsius. 540 calories of heat energy are needed. Heat energy is used to change from liquid to gas. Phase is called heat of evaporation. So, heat of evaporation from liquid to gas. So change 1 gram of water at 100 degrees Celsius to steam. So 540 calories of heat energy are needed. All the heat energy supplied is used to change the phase of the water from liquid to gas, not its temperature. So it's just used, the energy is used to change the phase of the water from liquid to gas and not its temperature. The temperature will not change until the water has changed into steam. Energy and phase change. So ice to melting to water to vaporizing to steam. So it takes more energy to change phase than to change temperature. When steam condenses to water, energy is released by the steam. So when steam condenses to water, energy is released by the steam. Or you can say emitted or emitted, release. When water turns to ice, water molecules release energy. So water turns to ice. Water molecules release the energy. Again, think of going from warm to cold or cool. From cool to cold. From cold to freezing cold. Problems, 540 calories of heat energy are needed to change 1 gram of water to steam. How many calories are given out when 10 grams of steam condenses? So 540 calories of heat are needed to change 1 gram of water to steam. How many calories are given out when 10 grams of steam condenses? So that's a multiplication problem. 540 times 10. You want to add your units. 540 calories times 10 grams gives you 5,400 calories. All right, a few more questions. What are the 4 phases of matter? Solid, liquid, gas, and plasma. Distinguish the difference between evaporation and boiling. Evaporation, you go from the phase of a liquid to gas. For boiling, you go from phases, changes with the temperature. So from cool to warm to hot to boiling. So it's a temperature change. Why does heating a solid make a meal? Sorry. Why does heating a solid make it melt? Heating a solid make it melt. So changes in temperature in the phases. Why does cooling a solid make it freeze? All right, so now let's go on. So that's kind of like the same thing. Cooling a solid, changing the temperature in the phase. Thermodynamics. So thermodynamics. First law, second law. Thermodynamics is the study of heat and its transformation to energy. So study of heat and its transformation to energy. The lowest possible temperature is absolute zero. The lowest possible temperature is absolute zero at 0 Kelvin or negative 273 degrees Celsius. Thermodynamics, so when a gas is heated, it expands. When a gas cools, it contracts. So heat up a gas and it's going to expand. Cool down a gas and it's going to contract. At 0 Kelvin, the volume would be 0. If the volume is kept constant, pressure is proportional to temperature. So at 0 Kelvin, the pressure will be 0. 0 Kelvin, pressure is going to be 0. It is impossible for matter to reach absolute zero. So that is impossible to reach absolute zero. Nana, your tush is in the way. So why is there a limit to coldness? Can't have negative energy, temperature. Whoops. I can't see Nana. Hold on, I have to go back to my slide. All right, so why is there a limit to coldness? Can't have negative energy temp. The atom would collapse or disappear. No volume or no pressure. So we're thinking about a limit to coldness. So you can't have a negative energy temp with Kelvin. And then the atom would collapse. So you can't have a negative number for Kelvin. It's 0, absolute 0. That's as far as you can go. Now, if you do the Celsius, you can have negative 273 degrees Celsius, you can do that, but not for Kelvin. For Kelvin, it would just disappear. So for the next one, the example is a flask of helium gas has a temperature of 0 degrees Celsius. So if a second identical flask containing an equal mass of helium is twice as hot, has twice the energy, what is its temperature in degrees Celsius? So a flask of helium gas has a temperature of 0 degrees Celsius. If a second identical flask containing an equal mass of helium is twice as hot, has twice the energy, what is the temperature? Nana, what's on your bottom? Did you go potty? You have to get your bottom cleaned off. Okay? I have to attend to my brother's cat. She needs some help wiping today. All right, let's see here. Consider a piece of metal at 5 degrees Celsius. If it is heated until it has twice the initial energy, twice as hot, its temperature would be 283 degrees Celsius. So consider a piece of metal at 5 degrees Celsius. If it is heated until it is twice the internal energy, twice as hot, its temperature would be 283 degrees. So you would need to convert to Kelvin. So 5 plus 273 degrees Celsius. So let's see, 273 degrees Celsius is equal to 0 degree Kelvin. And if you are all right, so 5 degrees Celsius, if you can, so 273 degrees Celsius is equal to 0 degree Kelvin. So consider a piece of metal at 5 degrees Celsius. So 5 degrees Celsius how much is that in Kelvin? So you just add 5, so 273 plus 5, 278 Kelvin. Now, if it's twice as much, so you take the 275 Kelvin and then times it by 2, which gives you 556 Kelvin. And if you want to convert it back to Celsius, then you'll do 556 and then subtract 273. And that will put it back to Celsius, which leaves you 283 degrees Celsius. All right, so thermodynamics, so internal energy is the sum of all the energy a substance has. So that's the internal energy. It's the sum of all the energy. Thermodynamics deals mostly with changes in internal energy, which is usually associated with changes in temperature. So thermodynamics usually or mostly deals with changes in internal energy. So internal energy is the sum of all energy that a substance has. So internal energy, which is usually associated with changes in temperature. So This is thermodynamics. So when heat flows to or from a system, the system gains or loses an amount of energy equal to the amount of heat transfer minus the amount of work done. So total amount of heat gained by the system, and then total amount of work done by the system. So change in internal energy. Increase the internal energy of the system. So the raise the temperature. You want to increase the internal energy of the system. You're going to raise the temperature. Energy remains inside the system. So there are two ways to increase the temperature of a substance. So the first law says to expose it to something that is a high temperature. So heat is added, increases the temperature, and it increases the internal energy. So when you add heat, you're going to increase the temperature and you're going to increase the internal energy. So this is part of the first law, work out. So do certain types of mechanical work on it, such as the compression. That's work going out. So higher temperature, decrease the internal energy of a system, lower temperature. So energy leaves the system. So there are two ways to decrease a substance. So suppose or expose it to something that is of a lower temperature. Expose it of something that is a lower temperature. So like an ice cube. You set like water on top of ice. It's lower temperature. So you lose heat. Because guess what? Heat is going to leave. Heat is going to exit out. It's going to emit itself to the ice cube. And so it's going to lose the heat and it's going to decrease in temperature and it's also going to decrease in its internal energy. Do work on things outside the system. So work done on the gas, work done by the gas. So there could be an outside part of the system, outside work expansion, causing work to be done on the gas. So when heat is added to a system, the amount of heat added can increase the temperature, can increase internal energy, and can do external work. Second law. Heat of itself always flows from a hot object to a cold object. So heat flows from hot to cold. Problems when heat flows from a warmer object in contact with a cold object. Do both objects undergo the same temperature change? So the warm object is going to emit heat to the cold object, and eventually it's going to cool down. So warm object cools, and the cold object is going to get warmer. So eventually both of these would be the same temperature. So change in energy would be the same for both. So they're both going to have a change in energy. So one of them is going to lose energy and the other one's going to gain. So change in temperature is not necessarily going to be the same. So the second law, heat region, cold region, heat engine, work out. You can have a heat pump. This is part of the second law, with work going out. And work can also go in. The second law of thermodynamics tells us that heat doesn't flow from cold to hot without external energy. So heat does not go from cold to hot without external energy. Consider a refrigerator in the kitchen on a hot day. If the refrigerator door is left open while it is operating, the temperature in the room will increase. Could you warm a kitchen by leaving the door of a hot oven open? Think hot to cold. Yes. Thinking about the refrigerator one, consider a refrigerator in the kitchen on a hot day. So you open up a refrigerator. You don't go from cold to hot unless there's an internal or external energy. Could you cool the kitchen by leaving the refrigerator door open and closing the kitchen door window? Kitchen door and windows. High quality energy, useful energy can't be used for work. It's concentrated or organized energy, but low quality energy is disorganized energy and is often wasted, so it turns into heat. So high quality energy is useful energy, can be used for work, but is concentrated and organized energy, but low quality energy is disorganized energy and is often wasted. In the natural process, high quality energy tends to transform into lower quality energy. So the direction of natural processes is from higher order to lower order. Second law, disorder can be returned to order, but only if energy is used to create the order. Nana, do you need some help? She's down there cleaning herself. I want to help her. So this will cause an increase in disorder somewhere. All right, so we're almost done here. So problems. So is the total energy of the universe becoming more available with time? As entropy in a system increases, energy in the system, what? So within a system, disorder increases, entropy increases, and the energy available to do work decreases. So highly ordered, think of the solids, disordered liquid, improbable way of bricks, at more probable way of bricks. Your room gets messier day by day. In this case, entropy is I would say increasing. Entropy, V equals D over T. Velocity equals distance over time. Our concept of time comes from the second law of thermodynamics. Time always points from order to disorder. And that's it. All right, so this video was a little bit shorter, but I do thank you for your time. I hope y'all learned something. All right, I'm getting ready to take my quiz here, 15 minutes. Oh, stretch. Oh, it feels so good. Oh, thumbs up if you like this video. All right, take care. I'm leaving. Until next time.